So now we will see when exactly will we need to analyze the algorithm. So to analyze the algorithm, there are two possible cases. One is when the input you pass is the worst possible input that you can give to the algorithm. And the next is the data in the algorithm is in its worst state. That is, the scenario itself is worst. In both these cases, we need to analyze and predict the time complexity of the algorithm before executing it. And to do this, we will use some mathematical notations. These mathematical notations are called asymptotic notations. The first one is big O. The definition goes as so. Big O of g of n is f of n such that there exists a positive constant c and n naught that 0 is less than or equal to f of n less than or equal to c of g of n for all n greater than n naught. What does this exactly mean? So we will see this from a graph here. This is the plot for f of n and plot for c of g of n, a random plot. So some graph f of n and some graph g of n, c of g of n. It's obvious that after a particular point, that is n naught, the plot for c of g of n should always go above the plot for f of n. This means that after a particular value n that is greater than n naught, that is for every n that is greater than n naught, we are sure that c of g of n is always greater than f of n. So this particularly gives us the upper bound for your f of n. That is, f of n at the max can only be c of g of n. It cannot go more than that. So this is the worst case scenario of a particular f of n. That is, if your f of n reaches c of g of n, that is the worst possible time your f of n can ever have. It cannot go beyond that. So while finding this c of g of n, we should make sure that it is the smallest upper bound that can be found. That is, you can have any number of bounds here which are above f of n, but c of g of n must be the smallest upper bound. There shouldn't be any other bound which is smaller than c of g of n which will satisfy the condition. So this is the smallest possible bound that can be given to f of n. We'll see an example for the understanding. I'll take a function t of n, which is n cube plus 3n square plus 4n plus 2. Now when our n increases infinitely, that is when the n value goes higher and higher, this value is too huge that the value here becomes insignificant while comparing to the value of n cube. So at any point in time, we can tell that n cube into some constant c will always be above the value of this function t of n. That is, t of n will always be less than or equal to n cube into c. It's similar to our upper bound definition, f of n less than or equal to c into g of n. So our t of n, that is, this is our function, can be told is equal to big O of g of n, which is our n cube. This means that t of n will never ever go above the value c into n cube. So this way we can find the complexity of an algorithm with mathematical notations from asymptotic notation. This is just the one notation you saw which gives us the worst case, that is the upper bound for your time. The next one is big omega. So the big omega definition goes as follows. Big omega of g of n is f of n such that there exists positive constants c and n naught, that 0 is less than or equal to c of g of n less than or equal to f of n for all n greater than n naught. Again we will see the graph. So we need a graph f of n and c of g of n, and from one particular point n naught, the value of your c into g of n must always be less than f of n. That is, after for n greater than n naught, the value of c of g of n is always below the value of f of n. So in other words, I will tell f of n at the least can only come up to c of g of n. It cannot come below that. So this is giving the best case, that is the lower bound for your algorithm. Whenever f of n reaches this, it will not be able to go beyond this. So this is the least possible time your f of n can run. Least time in the sense it is the best case for your algorithm. And while finding the best case, again we need to see that we are finding this as the greatest lower bound. That is, you can have so many bounds here which will still satisfy your f of n. But this must be the greatest one. Any other graphs here which satisfy the equation cannot be considered. So this is called as asymptotically tight, finding the greatest lower bound and the least upper bound. This is called asymptotically tight. So these values give you the upper bound and lower bound of your functions. As you know, big O was the worst case, big omega is the best case. So the next notation is big theta. This is your average case. As the definition says, again, so you can see here f of n is lying between c1 g of n and c2 g of n. Here c1 g of n will be your upper bound, c2 g of n will be your lower bound. Example here, say this is your lower bound and here it's the upper bound, and for after one particular time f of n will always be less than this and it will always be greater than this. That is, your f of n can only lie between these. So this will always give you the average case. So we saw three notations now. Big O, which is the worst case of your algorithm, the worst possible time your algorithm can take, and big omega, which is the best case of your algorithm or the least possible time your algorithm can take, and an average case, that is big theta, which will lie between two boundaries. So these are the three asymptotic notations. There are even further two more, that is little o and little omega, which we will see in the next video. Thank you.